Swayam Prabha. Digital India. Educated India.
Welcome to 17th lecture of video course on Tribology. Today's topic is liquid lubricants. In previous lecture, we understood solid and semi-solid lubricants, give merits and demerits. Today we are going to discuss most popularly classification of lubricant or class of the lubricant, which is a liquid lubricant. Liquid lubricants are classified based on their origin, whether they are extracted from vegetables, animals, crude oil, or they are made in lab. Based on their origin, we classify as vegetable oil. Typical examples are castor oil and rapeseed. Animal oil is maybe fish oil, whale oil. Mineral oil, which is the most popular and most economic category of this liquid lubricant. And finally comes the synthetic lubricant. We assume that synthetic lubricants are last source of lubricant. If we do not have any other option, we will select synthetic lubricants. Every class has its own merits and demerits. Talking about the vegetable oil, it appears to that this will be very economic, will be less costlier, but it does not happen to be. Processing takes time as well as money. So, they are not as economic as the mineral oils. In addition to that, they are less stable, thermal as well as oxidational. They deteriorate with increase in temperature and they get oxidized. When they get oxidized, their viscosity will increase, and if they thermally degrade, then there will be some deposits left with that degradation. However, vegetable oils have one good quality that is contained with more content than natural boundary lubricants. They are good additives for high load applications. Coming to the animal fats, one of the major drawback about animal fat is availability. With the stringent norms, government rules, it is very difficult to find out lubricants from animals unless available in one way or another form. Intentionally we cannot do things. Very positive point about animal fats is extreme pressure additives or extreme pressure qualities. They can sustain very high pressure. That is why they can be used as EP additives. Mineral oil is most popular, most commonly used, available in abundance, and from cost point of view, this will be cost and availability point of view, we will always vote for the mineral oil. Coming to the synthetic oil, say we can design any property in lab and utilize for the commercial purposes. The only problem is the cost. More and more processes involved, more and more design involved, more and more cost. Otherwise, any lubricant can be synthesized. Obviously, the lubricant can be synthesized for any applications. Major advantage which is generally quoted is the viscosity. Viscosity degradation is very low. viscosity index is generally higher than viscosity index of mineral oils. Few synthetic lubricants are slightly costlier compared to mineral oil, which can be utilized for common application. Otherwise, by and large, synthetic lubricants are costlier even 3 to 4 times compared to mineral oil. That is why they have restricted applications and they are used when we do not have any other alternative. One point I missed in this slide is Striebeck curve. You can see that we already studied this Striebeck curve. We say that x axis there is a Sommerfeld number, the viscosity of lubricant, sliding speed divided by average pressure. While coming to the x axis, coming to y axis, it is a coefficient of friction. You say as Sommerfeld number increases, coefficient of friction decreases to a certain level, and after that again it increases. And if I think about all these lubricants, I can place vegetable oil and animal fats somewhere in this region, or we can say the animal fat can be placed in zone 1. Coming to vegetable oil, it can be placed in mixed lubrication oil. Mineral oil somewhere here in zone 3 and some part of zone 2. So, based on the condition, based on the operating condition, we can choose a lubricant or we can mix lubricant. We say mineral oil can be mixed with animal fats, mineral oil can be mixed with the vegetable oils, or synthetic lubricant also can be mixed with other lubricants. Based on our application, we can choose proper lubricant based on Striebeck curve. One slide on vegetable oil and animal oil, such as a big subject, processing, how to get, how to do hydrolysis, and how to remove carbohydrates, vaporizers, contents, and use only content which are desirable. That requires a complete process. We are not describing that, we are not discussing that, we are just discussing a few important points. Sometimes this vegetable oil and animal oils are known as a fixed oil. Reason being, they do not vaporize during the operating conditions. They degrade, they decompose, but they do not vaporize. They volatilize, the volatility is negligible. That is why it is known as a fixed volume or fixed oil. And as I was mentioned earlier, they are made of the fatty acids and alcohols, or consisted of alcohols and fatty acids. Fatty acid work as a boundary additives. Now, what is the problem with their oxidation? They make a gummy substance which will stick to surface, reduce clearance. When the clearance is reduced, operating condition will change. If operating condition will change, it may bring much more difficult situation. So, as if I refer to the Striebeck curve, we can say a lesser and lesser clearance and more load will be applied on that, and it will turn out to be unstable system or unstable condition. Now, this last line of the slide says the fixed oil which are slow to dry are used for lubrication, or in other words, fixed oil, vegetable or animal oils which are slow to oxidize will be preferable lubricant compared to rapidly oxidized vegetable oils, rapidly oxidized animal oil. To reduce oxidation, need to be processed properly. To avoid the more complications, we can use fixed oil in mineral oils. Some of the example of the fixed oil are the given over here: castor oil, olive oil, we have heard a number of times, fish oil. They are good lubricant additives. They have a good lubricity, they stick to the surface, so they can be utilized as additive in mineral oil for lubrication purpose, for tribological purposes. Coming to the mineral oil, they are generally extracted, they are processed from the crude oil. and major constitute is a carbon and hydrogen. It's based, that's why we call it a hydrocarbon based lubricating oils. And see that carbon percentage is 83 to 87% and hydrogen 11 to 14%. This is by weight. To get a proper lubrication, often they are made with a long carbon chain. 30 plus is generally recommended for the mineral oils. In addition to carbon and hydrogen, they often contain sulfur, oxygen, nitrogen. This carbon chain of carbon and hydrogen, when they make bond, they can form in a straight line, they can be in a branch form or in a cyclic form. The property will change, the carbon structure is. The straight chain behavior will be one kind of thing. If the branched carbon chain, then behavior will change. If it is a cyclic one, then behavior will quite change. And based on the carbon structure also, they are classified. See that sometimes mineral oils are classified based on sulfur content. With more stringent norms, we require lubricating oil with a low percentage of sulfur. It's harmful substance, it pollutes environment. That's why low sulfur will be recommended or better. However, depends on the origin of mineral oil, from where they are extracted. They can be classified based on sulfur content. The Pennsylvanian oil, which has a low sulfur percent, will be recommended compared to Middle East, compared to Mexican. We say if sulfur content is lesser than 0.1%, that's the best, but for tolerable range it can be 0.1 to 1%. Beyond that, we need to have some sort of refining process to extract the sulfur from mineral oils. Based on the chemical structure, based on the branch form or straight form or cyclic form, we divide mineral oils in paraffinic oil, naphthenic oil and aromatic oils. One slide is given on the chemical formation. You see the chemical forms of mineral oil. You can see the simple straight chain. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen is completely straight chain. They will be more stable in this case. Here we have a second figure with the branched one. Carbon and carbon is making a branch. They do not have a same axis, but the lateral axis also been utilized. But one important point is that the chemical formula for first figure is a CnH2n plus 2. Our number of hydrogens are 2 times compared to carbon percentage, carbon molecules plus 2. While if the formula is changed, CnH2n, that structure also changes, and this kind of thing will be called as the naphthenic oils or naphthen, while first case it is a straight paraffinic oil, the branch paraffinic oil. I can verify very well that what are this structure. In first chain or first figure, we find that there are 7 carbon molecules or 7 carbon atoms in this case, but H is a 15 times, right. I can count this is a 1, 2, 3, 4, 5, 6, 7 and H will be 15 times, but there is a one vacancy over here. There can be a carbon, can be hydrogen. If it continues, finally will come one will be H. So, this formula will be satisfied. 7 carbon hydrogen is 15 and finally 1 will come, 15 plus 1, as a 16 is a 2 times of 7 plus 2. This formula is satisfied. Similarly, coming to the branch one, we have 11 carbon over here and H number of H are 23 plus 1. There is again vacancy over here. There is a one bond left, either it can contain carbon or hydrogen. If it is not containing carbon, it will be having hydrogen, then we will be getting 23 plus 1, 24. That means 11 into 2 is 22 plus 2 will be 24. So, both the structures are satisfying paraphonic structure. Coming to the nothing or naphthenic structure, we are able to see there are some complexity coming in this, and because of this structure, their pore temperature reduces, their solidification temperature is slightly higher. They will solidify comparatively some temperature which is higher than paraphonicus. I am just reversing. They have a low solidification temperature. They will solidify at a lesser temperature compared to the paraphonic oil. So, for low temperature application, naphthenes are good, but they will not be having that structural or thermal capabilities to sustain high temperature as a paraphonic oil. So, both have merits and demerits. Coming to the aromatic, what we find are the unsaturated. These bonds are unsaturated, can react easily with other agents, other chemical forms. So, aromatic are least preferred compared to the paraphonic and naphthenic. And in this case also we can count number of carbon particles or carbon contents, compare with H. We will find this is the 11 number of carbon, while H are 21 plus 1, there is a 1 vacancy here. It can be occupied by H or carbon for continuation. If it is a H, then it will be 22, that means 11 into 2 is 22. That formula is satisfied. Some merits and demerits of paraphonic oil. We say that paraphonic oil have a good resistance to oxidation. They are more stable against oxygen, but when they oxidize, they are no useful. They can corrode the environment or corrode the component which are in contact. In addition, they are not very thermally stable. When they are burnt, they make very hard deposits which can abrade the surface. So, the lubricants are used to reduce the friction and wear, but if we choose lubricant which is not thermally stable, burnt at high temperature, the temperature may be 150 degree, 170 degree, 190 degree, then they will make deposits, and presence of deposits, the clearance will reduce. In addition, there is a possibility of these hard deposits to act as abrasion, wear more and more. So, we select the lubricant for good reason, to reduce friction, to reduce wear, but because of the lack of understanding, if we select a lubricant which is not able to sustain that high temperature which is operating temperature, then they will form deposit on the surface, and it is often the case in engine. We find that the oils are making deposits on the surface, and we require additives to wash away those deposits. Coming to the second point, we say that they have a thermal stability, volatility is lower, they are not as fast degrading with temperature. So, viscosity index is high, is 90 to 115. Of course, this is a subjective, and few mineral oil have a lesser than few paraphonic oil have a lesser than 90, but we are leaving those exceptions. And in addition, they have a high flash temperature. Here it is says that the pour point is higher than naphthenic, the pour point where flow, they start freezing at high temperature compared to naphthenic, which was mentioned in the last slide also. That means, for cold applications, paraphonic oil will not be as good as naphthenic oils for low temperature applications. Coming to the naphthenic oils, we say they have relatively low VI, viscosity index, if I am very sure about the operating temperature, if I know the operating temperature is not going to change significantly, then I can choose naphthenic oils, particularly at the low temperature applications. However, this says that they have a good lower power point compared to the paraffinic oils. That is why they are good for the low temperature applications. In addition, naphthenic oil have one positive point: they do not make deposit as hard as paraffinic oil when they burnt. When naphthenic oils are burnt, they make soft deposits compared to paraffinic oil. So, they will be lesser wear tendency, or they will have a lesser wear tendency compared to paraffinic oils. But because of the deposits, and in addition when there is oxidation, they make a sludge formation, clearance will reduce, operating condition will change, and that is undesirable. Continuing with the mineral oils, not very high VI, not very high viscosity index, more tendency towards oxidation at moderate to high temperature. We use a multi-grade oils. Main ingredient is a mineral oil, but what we are trying to do, we are doing some sort of hybridization. Maybe one lubricant oil is good for the low temperature application, other lubricating oil is good for the high temperature application. We want to hybridize to come up with a result that lubricating oil is good for the low temperature application as well as high temperature application. An interesting thing is that when we go in a market, most of time available oils are multi-grade oils. Let us take an example as some sort of classification. Says that 10W30, W stands for the winter, and that divides. The left hand side of that is referred to winter oil, right hand left hand side of this W refers to the hot temperature condition. Or in another word, this multi-grade oil has a something like a SA10 characteristics as well as SA30 characteristics. By and large, when we are talking about second example, we say that it has also two characteristics. It's called SA20 and SA50 characteristics. That's why they are called a multi-grade oil. It's not a one single grade; it contains two grades. That's why it says that when tribo systems operate on a wide temperature applications, we are bound to use multi-grade oils. One typical example is given as aircraft hydraulic oil, which operates with from -40 degrees centigrade to 150 degrees centigrades. It's quite huge range, and most of the time mineral oils will not be very useful. We may require synthetic oils for this applications. But if the cost is a major consideration, then we can go ahead with some sort of multi-grade oil, and that's why it says that multi-grade oil shows one grade at the 0 degree Fahrenheit and a higher grade at the 210 Fahrenheit or 212 Fahrenheit. This is as I mentioned initially, the 10W30 the same example. So, the very high viscosity at the 0 degree Fahrenheit and SA30 characteristics as a 210 Fahrenheit. Whenever this kind of specification comes, we say that lower the first number, better will be the results at the low temperature conditions. Instead of 10, if we use a 5, that will have a better characteristics at the low temperature conditions. Similarly, higher the second number, higher the left hand side number, better will be the performance at higher temperature condition. So, in other words, if I say 10W50, that 10W50 will have a better performance at the high temperature compared to 10W30. Viscosity will be higher side. So, this is the multi-grade oil. Question comes, how to make this? Should I bring the two oils SA10, SA30? Okay, so 50% of SA10, 50% of SA30. mix it, use it. Is that work? Or we should use 30% of SA10, 70% of SA50. In reality, in practice, this kind of approach does not work. Simple mixing will not work. There are a number of methods, but one method which most popular method is adding polymers, adding additives in mineral oil. So, we add polymers in mineral oil to increase its temperature range. The question comes, how this mineral oil or polymers is going to work in mineral oil? This is schematic given in this slide. You say polymer, when they are in chain form, mix in mineral oil, they have a coiled characteristics. They will be in coil form. This is roughly a coil form, this is sketch shows. The polymers are in coiled form. They do not occupy much space. They remain in compressed form. As temperature increases, they change their form. Instead of complete coil, they open up, and with further increase in a temperature, they turn out to be fibers. And we have learned in a semi-solid, this kind of fibers give more resistance to the flow. They increase viscosity. So, this is how the polymers work. At the low temperature, they will not work, or maybe they are added in the mineral oil, they will increase slight viscosity because of this addition, but will not affect to a great extent. But as the temperature increases, the viscosity of the oil will increase. In other words, if I am using in a mineral oil viscosity will decrease with the temperature, but it is being compensated with increase in viscosity because of these fibers. So, one negative, one positive, it should give us the same results. Change in the temperature is not changing the viscosity. To demonstrate that in other way, we have one figure. I am assuming this is containing the lubricating oil. Now, if the temperature increases, so these dots are decreasing in their width, these dots are decreasing in width. That indicates that viscosity is decreasing with increasing temperature. So, this is increasing temperature side, viscosity is increasing decreasing in this way. But as we know, there is another constituent, there is an additive in this, which will also open up and with the temperature and increase viscosity, maybe some in this form. You can say there is a mineral oil thinned down, and this kind of fibers, they come in between to give more and more resistance to the flow of liquid, and to resistance to flow of liquid is known as a viscosity. That means, this kind of polymers are acting as viscosity resistant or resistance to decrease in a viscosity. So, I can say thermal thinning of the oil is being compensated by unwinding of polymer chain, and these are the multigrade oils. In reality, they are not mixed, they are not two separate oils, but they behave like, they show performance like two grade oils, like multigrade oils. Now, different kind of polymers can be used, which can show 3 grade oil, 4 grade oil, 5 grade oil, but we will be trying to show the performance of the extremes, lowest temperature and highest temperature, and based on that we can get a good results. Again, every advantage is not without any cost, or every positive point comes with some negative points. That is why we are discussing over here. Multigrade oil have some drawbacks. First thing is that they do not work as a Newtonian fluid. When mineral oil mixed with polymers, it will no longer contain a Newtonian characteristics. It will show a shear dependence. With increase in shear rate, viscosity of that oil will decrease. It will show a shear thinning behavior. That is why I say that effectiveness of the multigrade oil is affected by shear rate. The shear rate at which oil has to pass through confined space. Narrow space, convergence space, oil are pushed from that space and they will shear. They will reduce viscosity. So that at the high shear rate, viscosity of multigrade oil may be little or not different from the base oil. This is shown in this diagram. See that when shear rate is low, viscosity is high. Actual multigrade oil is working over here, but as the shear rate is increasing, they show a sudden change in behavior and try to reach the viscosity which of the multigrade oil, viscosity of the base oil or mineral oil in which the polymers are mixed. This loss in viscosity with increase in shear rate is governed by power law. That is why it is given on the logarithmic scale. So that with increase in a shear rate, initially loss of viscosity is not significant, but finite. It is not a straight line as is shown over here. There will be some loss, but there is again after that there is a sudden transition, and once this transition is over, it again reaches to the viscosity of mineral oil from where the multigrade oil was obtained, or main constituent of the multigrade oil. Mathematically, this can be expressed the way we have treated this as a semi-solid lubricant. Say shear strength, interface shear strength of due to the multigrade oil can be again given by the tau I. As initial some shear resistance is required to flow, it may be 0 also, and viscosity plus this is going to change. Here N will be by multigrade oil, it may be 0.8, 0.85, 0.9, depends on the kind of the polymers mixed with that. Sometime we use this lubricant or this lubricant relation. We say that there is a shear stability constant K. Shear rate is given. It can be one dimensional, it can be two dimensional. What we have considered previously examples, mostly we assume that relative velocity or sliding velocity is only in one direction, that was x direction, that is why the velocity was expressed in by u. However, for general application, when velocity is in x direction as well as the z direction, then shear rate in y direction can be expressed by first term and then shear rate in second or z direction can be expressed by second term. This shear rate can be substituted, whatever the value we know, if the operating conditions are known to us, we can substitute it here. This is viscosity at a high shear rate. It is more like a ascent diagram for the fatigue loading. Initially no change, then suddenly change, and after that reaching to one knee formation, a constant value, where the mineral oil is not dependent much on the shear rate. It works as a Newtonian fluid. Or we can say in other word also, this mineral oil is a mix with the polymer additives can show two kind of Newtonian fluids. High viscosity Newtonian fluid initially at the low shear rate, and low viscosity Newtonian fluid other rate, and in between transition can be transition behavior can be obtained by using this relation. If the viscosity or with the shear rate is lesser than this limit, then it will be high viscosity Newtonian liquid, and if shear rate is more than this limit, then it will be high viscosity low viscosity Newtonian fluid. In between that shear rate, whatever the In this example, we are saying that 10^3 to 10^6, but not necessary for every oil will be 10^3 and 10^6. It can be different. Now, if I use high shear rate in this case, then the relation will be always turning out to be equal to the viscosity mu 2, because mu 1 will be cancelled out, and if the low shear rate, then it will be the mu 1. We can substitute and we can find. It depends whether this parameter is very high or low. If I assume the shear stability parameter is 0, that means this multigrade oil is working with a viscosity equivalent to mu 2. Now, if the K value is very high, then this multigrade oil will remain for the longer duration for much higher shear rate. So, in other words, this shear stability parameter, higher the value, better will be the results. Even if I use the multigrade oil 10W40, in one case the K1 turn out to be 20,000, in other case for the same specification K1 or K turn out to be the 50,000. So, in that situation we say the 50,000 value of K equal to 50,000 will be preferable option, preferable multigrade oil compared to 20,000 value of K. So, based on this shear stability parameter, we can choose multigrade oil. Otherwise, for the specification, both oils will be 10W40, we will not be able to distinguish much. From one company to other company, the distinguish can come using the shear stability parameter. Now, final one comes on liquid lubricant is a synthetic oil. So, that major thing is expensive because it is being designed for major companies who have a very high production. Overall cost may come down because of the design cost will be only one time, after that only fabrication or synthesis cost. But for the new applications, this will turn out to be very costly affair. And we say that because of the cost, these oils should be used whenever mineral oil are inadequate. Either they have this more tendency of oxidation, there is a more tendency of a viscosity loss, there is a more tendency of explosion, there is a more tendency of solidification. In those situations, synthetic oils should be utilized. Otherwise, mineral oils are very cost effective. Those oils should be utilized with either a pure form or with some sort of additives to give extra properties. Typical situation where the synthetic oil is used is given as a jet engine. The temperature you can see the minus 120 Fahrenheit. Operating speed very high, the 60,000 plus, and exhaust temperature of that engine is more than 500 Fahrenheit. In this situation, mineral oil with all kind of additives may not give very good results, may not give desirable results to us. And that is why I say that synthetic oils are engineered. Reason being, as they are engineered, they will be uniformly shaped molecules. That is why we will be having much more robustness than mineral oils. And they are generally made with a low carbon chain, so that they have more heat and stress stability. They have much more strength. However, their lubricity property will go down with a low chain. That means they are good for high speed applications, where there is a more possibility of hydrodynamic action. For high temperature, but separation is not a problem, but the high temperature is a problem. So, based on requirements, synthetic oils can be selected. There are a few synthetic oils which we are describing here. Otherwise, there is a complete subject also on a synthetic oils, more on chemistry side, more on chemical engineering side. We say first common category is polyglycols. VI is almost 200, and they have been utilized in a brake as a brake fluids. We try to utilize this kind of polyglycol in our magnetic bearing setup, where desire was low lubrication requirement and film thickness was maintained by the magnetic repulsion. If we would have used high viscosity oil, there would have been much more shearing of that oil, much more heat generation, but we use a brake fluids which have low viscosity, and what we have used a viscosity equal to the 2 centi-stroke at 100 degree centigrade. We run that setup for the 6000 rpm for almost 3 to 4 hours, and we found not even single degree temperature rise. Reason being, magnetic levitation was there, and even though there was a problem created for the hydrodynamic action, but there was clear separation between those surfaces. So, for high speed applications, this kind of oils can be utilized. They have very low viscosity, which is always desirable for high speed applications. And another thing is that they have a good cooling capabilities, so which are desirable. In addition, if they have a high temperature application, if they start burning, they do not leave any debris after that, they do not leave any deposits. So, they are clean liquids, vaporize, they do not show that they were these kind of lubricants were there in that domain at all, then regime at all. So, they can be utilized for the textile industries where the cleanliness is a prime requirement. Other kind of low cost lubricants, synthetic lubricants, are the esters. Can be made by alcohol on inorganic acids. They are much cheaper than other synthetic lubricants, but they show good performance. They show the lesser friction, lesser oxidation, is more resistance to the oxidation, and because of that good resistance to oxidation, their draining time during draining period is large. Obviously, that they do not require frequent replacement. Draining period during draining duration is large. They do not vaporize easily as a mineral oils. As I mentioned, they are less costly compared to a number of other synthetic oil. That is why they are popular, and you can say that they have a cost more than mineral oil, but they are not to significant level, it is only marginal level. Silicon oil, very costly liquid, very good high VI, they are much more resistance to temperature thinning. The viscosity does not decrease that much. In addition, they are chemical inert. So, wherever there is a tedious or there is a cumbersome environment, or there are high temperature applications and reactive environment, we can choose silicon oils, but they have a low boundary additives, or if boundary performance is low, their oiliness level is negligible, they do not stick to the surface. They can be used as a lubricant. So, if there is a hydrodynamic action, this should be used if cost permits. Most often they are used, this kind of lubricants are used for the space applications. Keep in mind, silicon oils are always required with a good design, good understanding of the system. If we do not have very good design, assume that lubricating oil is going to deal with all the situations, that will not work, particularly with the silicon oils. There are two similar kind of the perfluoropolyalkyl ether, perfluoropolyethers. Their VIs are high, they have very good thermal and oxidational stabilities, even can be used in vacuum applications. can see perfluoropolyethers, the temperature limit is 320 degrees centigrade, same as a silicon oil. They are also chemical inert. If they are chemical inert, they will not react with the environment easily. So, they are good lubricants, high temperature lubricants, and cheaper than silicon oils. So, this kind of lubricant be selected as per our wish, as per our application, if the cost is permitting us. There are few remarks when we choose or use the lubricants. First remark is on the grease. Good point is that it adheres to the surface, it covers the surface. So, gives a good protection against the environmental contamination, but they are restricted to the speed application. Higher speed application, there will be very high thinning of the grease, or is that there will be bleeding of the grease. That is why the speed limit many times is kept at the 2 meter per second, except the few rolling mills or rolling element bearings, where the speed limit is slightly larger because of the rolling action, but in sliding condition, no. Major reason given for this is inadequate heat dissipation. Their thermal conductivity is negligible. They can't dissipate, they cannot conduct heat properly, they cannot convect heat properly. So, this kind of greases will not be having mode of heat transfer. Coming to the liquid side, you say that prefer low viscosity oils. Major reason, there will be lesser shearing. If the Newtonian fluid, we can say shear stress is proportional to the viscosity. Lesser the viscosity, lesser will be the shear resistance. Lesser the shear resistance, lesser will be the friction force. Lesser the friction force, lesser will be the heat generation. So, low viscosity oils should be preferred compared to high viscosity oil, provided minimum film thickness is maintained. Now, these low viscosity oils are also preferred from the cooling point of view. That is why I say they can carry the heat. In addition, they are preferred from the feed pressure point of view. If we are trying to levitate one surface over other surface, or keeping a separation between the surfaces, sometimes we force feed the lubricant and pressurize the lubricant between the two surfaces. In those situations, again the low viscosity lubricant will be preferred, because the high viscosity will give more resistance to pumping, and more resistance to pumping means there will be more power consumption. So, cost of power loss will increase, we say power loss will increase, the cost will increase. However, if this low viscosity oils, they are not able to give good performance because of the high load condition or slow rubbing speed when the hydrodynamic action is not made, then we can use additives, or we can add additives. In this case, we say mineral oils can be combined with the boundary additives, or we say can be mixed with the EP additives to give the desirable results to us. Final one, after liquid lubricant comes a gas lubrication. We have only one slide because the gas is not intended lubricant unless it is pressurized. So, that when we are talking the gas, it can be anything. It can be environmentally available air, it can be nitrogen, it can be helium. We know the helium has a good levitating capacity. Major or main important point of the air is temperature range. Temperature range may start from minus 200 degrees centigrade to 2000 degrees centigrade, and the major thing is there is no vaporization. It is advantageous to us. there will not be any cavitation. When we discuss the application of the liquid lubricant, we will discuss about the cavitation also. There is no problem related to solidification unless the temperature is very low, and there is no decomposition also. So, it is away from all those problems. Related to viscosity, it has a very low viscosity, will not give much problem. Relatively clean, they do not require seal unless we are pressurizing, we are sending we are passing air or helium or nitrogen at some pressure. Of course, if the environmental issues are related, then seals will be required, but not from an operating point of view. But there are some drawbacks. We say this kind of lubrication is effective when the load requirement is not very high, applied load is very low. We do not require any damping, or there is no vibration related problem, and even ultra thin film thickness is sufficient to separate two surfaces. That means, we require very good softness of the tribose surfaces. Now, this is imposing major design problem. If surfaces need to be very smooth, and by the way, if they come in a contact, there will be very high adhesion. So, gas lubrication require extreme optimization with all calculation of unevenness, or we say that all situation, in all the situation it should be working, otherwise it will turn out to be unstable situation. Slight change in the load, it may collide, or surfaces may collide together, or one against each other, and there will be high adhesion between surfaces. That will be problematic. That is why I say that it is a less forgiving of the errors in estimating the loads. The load estimation is not proper, then there will be problem. These bearings are highly optimized. Once we have a thorough understanding of complete system, load, speed, temperature, variation in the load, variation in the speed, then only we should be able to utilize air bearing. Talk about the rheometer, where we want to find out the actual measuring torque, or whatever the torque in equipment we want to measure that, or torque resistance given by the fluid. We require extremely good bearings. In those situations, these air bearings can be utilized. They are very sensitive towards operating conditions. That is why once we know we have a thorough understanding of systems, then only we should utilize this. Sometime we, to tolerate this kind of transient conditions, we mix solid lubricants. Of course, mixing solid lubricant does not mean that you have to mix in a gas. What we apply as coating, solid lubricant coating on the surface, a 15 to 20 micron coating, that will give extra smooth surface. Even the two surfaces are coming in collision or coming in contact, they will not wear away easily because of the solid lubricant, which because of the junction formation will be low shear strength junction. That will be good option. Maybe they mix solid lubricant with air lubricant, or apply solid lubricant on the surface and then operate on air related operation, either aerostatic or aerodynamic conditions. Now, this overall selection criteria for choosing the lubricant, we say that there are this slide has one arrow which indicating the increasing the speed. Just opposite side there is one arrow which shows increasing load. That means increase load and speed, they are contradictory. The higher speed will give different choice and higher load will give different choice, and they are always in contradiction. So, this meaning that if there is a very high load and low speed application, we should choose a solid lubricants. After that, number of grease comes. We say that moderate load and moderate speed. Similarly, high viscosity oil is a moderate load, moderate speed. Low viscosity oil, low load, low speed. Coming to the gas, which is the extra low load, very low load, very high speed. Based on this, we can choose lubricant, whether we opt for the solid lubricant, grease, semi-solid, high viscosity oil, low viscosity oil, or gas. That is why we say that whenever the selection comes, the two major criteria will be the load as well as the speed, and both the criteria are pointing to the temperature rise. High load, even the low speed, will give high friction force, high heat generation, high temperature rise. Same thing with low load, but high speed, again the temperature rise will be larger, and this can be given operating temperature can be given by this relation. So, coefficient of friction, higher coefficient of friction means high temperature. High temperature means we should go for the low viscosity oil or the gas. High force, again high temperature. In this situation, we need to tolerate, whether we need to combine two lubricants. High velocity, again we have a high operating temperature. So, we choose a lubricant accordingly. The two factors, in addition to this, mu, f and v are given as area. Larger area, lesser will be the operating temperature, because there will be more dissipation area available, heat will be dissipated easily. In addition to that, last parameter comes, that is a K, that is a conductivity. If the mating surface have a good thermal conductivity, then operating temperature will be low. In another short word, we can say, if the operating temperature is low, then we can choose a low viscosity oil or the gas. If high temperature, which is going to reduce the viscosity of oil again, in that situation we choose a high viscosity oil. So, it is slightly complex. More load, we should choose semi-solid and solids, but that is going to increase the temperature. If the increase in a temperature, if it is reducing this the viscosity of the lubricant, then we should choose some sort of additives. And this indicates that study of the additives along with this kind of lubricant is essential. So, that will be our next lecture on relating to the additives. We will discuss about the lubricant additives. Thanks for your attention.